Hello students, welcome back to control system class. In the earlier classes, we have focused more on mechanical systems. We have found the transfer function for it. Then we moved on to something called analogous systems, that is electrical analogous systems for mechanical systems. So that puts an end to the first part of first unit. Now we will be moving on to second part of the first unit. The second part focuses mainly on two things, that is block diagram reduction technique and signal flow graph. These are the two techniques available for finding the transfer function of a given complex control system. So in this video, we will be focusing on block diagram reduction techniques, that is the basic rules that we have to follow for block diagram reduction. So let's get into the session. In this session, we will be dealing with block diagram reduction techniques. Block diagram basically is a pictorial representation of a control system. This gives information on the subsystems involved in the entire system, the direction of flow of signals, and how all these subsystems are connected so as to form the entire system. So all this information will be available in the block diagram. Using block diagram, we can find the transfer function of the entire system, provided we have to follow certain rules. So in the next few slides, we will see what are all the rules that we have to follow while reducing the block diagram so as to find the transfer function of the system. Before we enter into the rules of block diagram reduction, we will see what are all the components of the block diagram. We have four components. The first one is simple blocks. These blocks represents the subsystem involved in the control system. So this subsystem has the output y and input x. So the transfer function will be y of s by x of s, which is represented by g of s. So like this, we will have many small subsystems involved in the entire system. And we will have arrow marks. Arrow marks represents the direction of flow of signals. We have two more components, that is the summing point and the branching point. The summing point is a point where you add two or more signals. For example, in this adder, we have added u1 of s and minus u2 of s. That is, we have subtracted u1 of s minus u2 of s. So the output will be u1 of s minus u2 of s. If it is a plus sign here, then the output will be u1 of s plus u2 of s. You can have even another signal coming here, and along with sign if you give, then three signals can be added using a adder or summing point. So this is a part of control block diagram. There is also something called branching point. Branching point is nothing but a takeoff point. That is, if you have a main line with the signal U of S flowing, and when you tap a line like this, that means that in this line also there is a signal U of S, and this U of S can be given to any other subsystem. So this branching point is used for tapping the signal. This is called as branching or even a takeoff point. So these are the four elements involved in the block diagram. So coming to block diagram reduction rules, when two blocks are cascaded, that is when they are in series, then you, instead of writing it as a separate G1 and G2, you can combine it to one single block with the transfer functions of each and every block getting multiplied, that is G1 into G2. This is the first rule, that is combining two blocks in cascade. If there are two blocks G1, G2, then you can write it as a single block G1 into G2. For example, if there is a signal U flowing, then the output of this block will be the signal U into G1. So here you will get U into G1. When U into G1 is given as an input to the second block, then the output will be U into G1 into G2. So similarly, this is equivalent to this diagram. That is, if U is the input and when G1 into G2 is the transfer function of this block, then the output will be U into G1 into G2. So either you can write it like this or you can reduce it to this form. The second rule is combining two blocks in parallel. When do you call two blocks in parallel? That is, if the same signal flows into the two blocks and the output of the blocks are getting added, then you call the two blocks as blocks in parallel. So you can see here U1 flows to G1 as well as to G2. The output of this subsystem, that is U into G1, and the output of this subsystem, that is U into G2, gets added in this summer. So these two blocks are called as blocks in parallel. Instead of the entire block, you can replace this block by writing G1 plus G2. If you are adding, if both the symbols are plus plus, then it is G1 plus G2. If you have plus sign here and minus sign here, then the block will have G1 minus G2. So when the input is u and when the transfer function is g1 plus g2, then the output will be u into g1 plus g2. So instead of this entire block, you can replace this one with a single block. That's what is the second rule, that is combining blocks in parallel. This is the third rule, that is interchanging the summing points. You can interchange two summing points if you don't have any element in between. That is, if you should not have any element in between the two summers, and you should not have any branching point also in between the two summers, then you can interchange the two summing points. You can see here how we have interchanged. The C wing has come to the left hand side and the B wing has gone to the right hand side. Still the output remains the same. In this case it is A plus B plus C. Here in this case it is A plus C plus B. So you can interchange two summing points. Similarly, you can interchange two branching points if you don't have any elements between them. That should be noted. You should not have any elements between them. Then you can interchange the two branching points. This is another rule regarding moving the summing point towards the right of a block. When you move a summer towards the right of a block, then that particular wing has to be multiplied by the block's transfer function which you jump. See here you have jumped G. So this wing has got multiplied with G. Can you see that? This summer jumped to the right hand side. So this wing which jumped this block is now getting multiplied by the transfer function of the block which it has jumped. So now let us check in both cases whether the output is same or not. See here it is u1, u2. So suppose if it I neglect the minus sign, here you will get u1 plus u2 multiplied by g. We will get g into u1 plus u2. Here in this case also this u1 is supplied to g1, so here you will get u1 into g. Since we multiply this wing with g, u2 is multiplied with g, so here it will be u2 into g, and when you sum it together you will get it as g into u1 plus u2. Both cases you can see that the output is kept the same. So this change is required when you jump. That's the point actually. When you jump a block, then this particular wing has to be multiplied by g. This is about moving a summing point towards the right of a block. Similarly, when you move this summing point towards the left of the block, then obviously then that particular wing has to be multiplied by inverse of the block that you jump. If we move this summing point towards the left of a block, then that particular wing has to be multiplied by reciprocal of the block that it jumps. So here it has jumped from right to left. So this wing is getting multiplied by 1 by g, that is the reciprocal of the block it has jumped. So in the both the cases you can see that the output is maintained as u1g plus u2. In short, summing point moving towards the right, multiply it by the transfer function that it jumps. Summing point moving towards the left, multiply the wing with uh, reciprocal of the transfer function that it jumps. The next two rules are regarding moving a branching point towards the right and branching point towards the left. When you move a branching point towards the right of a block, then that particular branch which you move towards the right of the block has to be multiplied by inverse, that is reciprocal of the transfer function that you jump. So here you can see that it is this particular point has jumped to the right hand side, and that wing was multiplied by 1 by g. That is the reciprocal of the transfer function, it has jumped. So conversely, when you move the branching point from right to left, then that particular branch has to be multiplied by the transfer function that it jumps. So you can see here the right hand side branching point has moved to the left hand side, and the wing is getting multiplied by the transfer function it jumped, that is g. In both cases, you can see that the output is maintained the same, u1 into g, u1 into g. The output coming out of this wing, it is u1 into g. Here also it is u1 into g. Similar is the case here, u1 into g, it is u1 that is getting tapped. So when you multiply it by 1 by g, then only it is this particular wing's output is maintained at u1, because here you will get u1 into g. When you tap it, u1 into g, when it multiplied by g, g gets cancelled, and the output of this wing is kept at u1. That is the same as this left hand side case. So this slide is regarding movement of a branching point towards the right and left of a block. Here you can see that there is a feedback part. This is quite important because there is an input u and there is an output y, and from the output the signal is tapped and it is given to the input through the feedback element, that is the transfer function of the feedback is h of s. So once you get y of s here, that gets multiplied with h of s. So you get here y of s into h of s, that goes as a negative feedback to this system. So u of s minus y of s into h of s will be equal to e of s. This e of s getting multiplied to g of s will be your y of s. So whatever I said, it is written here, y of s is equal to e of s into g of s, and e of s is substituted with u of s minus y of s into h of s. So once you reduce it, you get y of s by u of s as g of s divided by 1 plus g of s into h of s. This is a very important rule. That is, when you have a feedback loop, that is a negative feedback, this entire feedback loop, that is the entire block, can be replaced with one block with the transfer function g of s divided by 1 plus g of s into h of s. That is, g of s is the main block's transfer function, h of s is the transfer function of your feedback loop. So this entire unit, that is g of s, h of s, along with this summer, this can be replaced by a single block which is given the transfer function, that is or which is given the value g of s by 1 plus g of s into h of s. So this rule is very important. If it is a positive feedback, here you will have 1 minus g of s into h of s. If it is a negative feedback, it will be 1 plus g of s into h of s. If it is a positive feedback, it will be 1 minus g of s into h of s. So these are the few rules that we are going to use in future to reduce the block diagram.